Hello, everyone. Let's look at another method on how to solve a system of linear equations through using determinants, also specifically by Cramer's rule. So starting off with that, there is the standard matrix equation. And looking at that, that's the D times X equals B, where we're talking about the determinant that cannot equal 0, of course, otherwise there wouldn't be a solution. But we can break this down and figure out the pieces. Now, as you're probably aware, there's many ways to solve a system of equations. This is just another method, and it's specifically called Cramer's rule. So starting off, to do that, to find the x value, we would find the determinant at x divided by its overall determinant. And we would do that for position 1, 2, and so forth all the way down, where the matrix is obtained by replacing that column of the matrix or determinant by a n by 1 matrix. In other words, we're going to be using our ending total matrix for replacement. So it's easier by showing how to do that. So let's look at the first example. Using Cramer's rule, let's solve this item. So the first step is to change it into a determinant, and it's going to be a 2 by 2. We're only including the left-hand side of these equations, the x and the y values, not the total value at this time. We're only looking at the variable coefficients. So let's start off. We're going to take the coefficients of the x column and the y column and put them in as a determinant. Again, a 2 by 2. To find its overall determinant, it is down diagonal minus up diagonal. And we get 10 as the overall determinant for the system. Then the next thing we're going to do is we're going to replace each column X and column Y separately with what is called matrix B. Well, matrix B is really the total matrix, which is, let me just scroll back up here. The total, that's the constant over here on the right-hand side of each of the equations. So my matrix B will equal its upper equation total of -1 and the second equation total of 2. Now, this matrix B replaces column X if we're finding the D of X determinant. So again, just replace this whole column with matrix B, and then it's a 2 by 2, and we do the same thing. Downhill minus uphill gives me a total of a -20. And then I do the same thing for Y. So the Y column, I replace it with matrix B, and I get downhill minus uphill, and I get 5. Now this is only the first piece of the item. This is solving for overall determinant of each value part, an x and a y, and then we would go to step 3. Let me scroll down. We would find the solution by taking each individual determinant found, such as the d of x, d of y, and such, and divide by the total determinant found in step 1. So again, for my x value, we find that total determinant of x was -20. We divide by its total determinant of the whole thing, which was 10, and I get -2. And then same thing with the y. I had 5 for the determinant of y, and out of the overall determinant of 10 gives me 1/2. So our solution set, our x, y, is a -2, 1/2. And we have found the solution of that item. We could have found solutions in other methods, such as substitution method, elimination, as a regular item, but we now can use Cramer's rule to also find the solution. And remember, the solution set of two linear equations is where they intersect. It's where they meet and overlap. Now, what happens if it's bigger? So example 2, we're going to use Cramer's rule again, and this is going to be a 3 by 3. Now, as a reminder, when we're finding the determinant of a 3 by 3, we also have to use our sign matrix. So we have first step, the same thing we did in example 1, is we're going to find the overall determinant. Now I would choose either row 2 or 3 or column 2 or 3 because they both have zeros in it. They would allow one of the items to be canceled out. So same method as we did before, finding the determinant in the last unit that we just went over, but we would have the positive from the sign matrix, the 3 as the scalar, and then eliminate the row and column the 3 is in. That leaves these 4 numbers would be the 2 by 2 determinant piece. Go through there, downhill minus uphill, and we get through and we find that the overall determinant is a negative 38. Sorry that this got cut off. And then continuing down, find all the individual determinants with replacement of the matrix B. Remember, matrix B is your total constant matrix from our original, and it had its constants of 1, 0, and 5. And then you get to choose which one you're going to do. Now, with d of x, when I replace this first column with 1, 0, and 5, I have row 2 that has double zeros. I chose row 2 because it would be the easiest for me, where I only have one piece that I'd have to actually calculate, because 0 times anything is 0, 0 times anything is 0, and so it's really just that third one. And remember, this was a plus, minus, plus, minus, plus, minus. So this is a negative, and then a 6 times, cut out those pieces, I have 1, negative 3, 5, negative 2, downhill minus uphill, and I get a negative 78. You would do the same thing for the y and the z with replacement. Go through whichever one you're going to choose. I didn't show all the work on these two, but those are the numbers that come out. Now remember, before we had to take its individual determinants divided by its total determinants. So scrolling down, that's where Cramer's rule comes in. And if I just want x, I take the determinant of x divided by its overall determinant, and I got a fraction, which is fine. It's 39 over 19 reduced. You need to always reduce in lowest terms. Y is the same thing. Again, same method for z. And then your solution set, if it's in matrix format, would go x, y, z, and this is the reduced in matrix form. Now, sometimes you'll also see it written in standard form, and as you know, standard form goes in x, y, and z, and that means it's that location of the three planes where it ended up meeting, in this case, 3 lines, end up having the same solution at that one location. Hope that helps. Good luck with your studying. Until next time.